Welcome back to Computer Science 4303. Today we are here at lecture number 5, which is space representations, and we're talking about one of the simplest possible representations for spaces in games, and that is grids. So grids are a really cool data structure. They use a little bit of memory, but they're going to allow us to do some really cool stuff. After we talk about what grids are and how they can be used in this lecture, in the next lecture we're talking about some algorithms that can be done on grids. And then based on today's lecture and the next lecture, next week we're going to be starting assignment 2, which will be all about implementing the things that we learned in these 2 lectures. And just in case you didn't realize, yesterday I did a bit of a bonus lecture, which was a tutorial, and it's linked down here in the spreadsheet, and it's how to use VS Code with C++ and Makefiles. And that can be used for this assignment, for this course, and all the assignments in the course if you want to. So that goes over what Makefiles are, what VS Code is, how you can use them together in order to have a really good time in the course and have a more of a sort of an integrated experience for all the people in the course, rather than some people using Visual Studio, some people using Xcode, some people using the terminal, etc. All right, so make sure you check that out if you're interested, and let's get on with the lecture for today. So today we are talking about space representations and specifically the grid representation for spaces in our games. So let me very quickly make this. There we go. So, how do we choose to represent the game world space for problems like pathfinding, for example? Okay, so this space representation, I'm going to be talking in terms of pathfinding today, but the problem that you're attempting to solve doesn't necessarily have to be pathfinding. It's just that pathfinding is sort of this canonical example for video games, probably the most important example, but you could also use all of this knowledge for things like combat or strategy in a game as well. It doesn't have to be used strictly for pathfinding. So space and action representations are important decisions, and the ideas are linked together. And which representation we choose, and remember we talked about this a little bit in the last lecture, is based on factors from the game's design. And so the choice of space representation in the pathfinding engine will determine the movement actions that can be performed. So this is a little bit of a recap from last lecture, but I think it's important to repeat again. So what are some of the considerations that we have to make before we choose a space representation in our game? Well, first is localization. So for example, how do we find where an object is in the representation, right? So for example, do we just have an XY location? Do we have a cell in a grid? Do we have a node on a graph? So how do we want to localize ourselves within the space that we're representing? Generation. So how is this representation generated, for example? Like, how do you overlay the grid on your map? How do you talk about the graph? What are the nodes? What are the edges? How is all of that generated? Is that something that you have to do manually, or is it something that you can do automatically? All of these are important considerations. So dynamic changes. So how would you handle changes in, say, the world geometry, right? So for example, if you have an obstacle in your level and that obstacle moves, how does that get updated in your representation? Are you stuck? Or do you have to recompute the whole thing? Can you just change one of the cells in the grid? That's an important consideration as well. Planning and pathfinding. So how are your actions computed or represented, right? So for example, if we have a grid structure, we can talk about things like up, down, left, and right. However, if we have a graph structure, well, up and down don't really make sense. Now we have to talk about moving from nodes to nodes on a graph, right? So that makes that's an important consideration as well. And possibly one of the most important things is how much memory and time are required to compute paths in your game. And again, this is not just for pathfinding, but you know, if we're considering attacking the enemy base, how much time and memory do we spend on that computation for attacking, right? So again, a little recap from last time. we talked about different representations that we can have. Well, one of them is sort of this arbitrary precision representation where just everything is a floating point number and we sort of move around in floating point space. We could have a grid structure like we're seeing here, a graph with nodes and edges sort of representation. We could have a polygon representation, or a bit more of a special case of a polygon representation is a triangular representation, okay, where all the triangles are then nodes on a graph, etc. It turns out that Starcraft 2 uses triangulation for its pathfinding. So this is actually a screenshot of how the map gets processed in Starcraft 2. And you can see here that the map is broken down into all these different triangles, and then paths are computed as waypoints through these triangles. We talked a little bit last time about Navmesh representation. And so Navmesh really can incorporate things from all of these, right? Like a Navmesh doesn't have to be a grid type structure, but in this case, it is a grid type structure, right? So we talked about navigation meshes, what they are, and how they were formed. So we have lots of possible space representations that we can choose for our games. But in this lecture, we're going to be talking about grid representations. So, a grid, in the context of this course, is a 2D structure that divides the world into equally sized cells, okay? It's, in my opinion, the simplest type of method to implement for a space representation, and it's typically used to represent 2D surfaces. It can definitely be used to represent 3D surfaces. You could talk about voxels, right, instead of cells. But in this course, we're going to be sticking to 2D representations. However, the algorithms could be applied to three-dimensional spaces as well. Grids are used in many games for a lot of things. Just some of the examples that I'm going to use in this lecture would be like RTS games, so like Warcraft and Starcraft, as well as RPG games like Dragon Age, for example. So grid representations use grids, or 2D arrays, essentially, to abstract the space so that certain tasks are simpler for our algorithms. And so the idea is that we're going to have some algorithms that are going to run instead of in the actual game coordinates. So this algorithm that we choose may have initially had to run on like an arbitrary precision. Now we're going to run on a grid instead. Okay, and usually we'll find that running on a grid is going to be a little bit simpler than running on arbitrary space. All right, and oops. These grids, as I sort of alluded to already, they can be implemented by a 2D array or a vector internally, right? So if we look over here, we've sort of, we have this little imaginary space, and if we want to represent or store the data for our grid, we're probably going to end up doing that with some sort of 2D array or 2D vector within our actual implementation. And grids can be used for many, many, many types of tasks, okay? Not just pathfinding. I'm just going to show a few of the possible ways that you could use grids in various games. So Starcraft uses grids in a bunch of different ways. I know Starcraft is a bit of an older game, but the same goes for Starcraft 2. So for example, in Starcraft, the game is broken up. Well, in Starcraft, you can use, grids are used internally. Excuse me for jumping all over the place. Starcraft internally uses grids for different things. So one of the things it uses for is for building placement. Okay, so buildings have a certain size in the game, and they are placed at a sort of abstract resolution. So in StarCraft, you cannot place a building arbitrarily in the level. It has to sort of be aligned to what they call the building grid in StarCraft. There's also a walkable grid in the map representation, and that shows exactly where in the map the units can walk or they can't walk. So let's dive down into this a little bit deeper, because in StarCraft, in this course, we're going to be using StarCraft for our project, right? So let's talk about the grids in StarCraft just a little bit more detail, and how you can use them for various purposes internally for computing game logic or physics or actions, etc. So in StarCraft, there are three separate sort of resolutions that these grids operate on. So the game operates internally at a pixel level resolution, okay? So you see here these sort of red, I apologize for anyone who's colorblind. These red boxes represent the collision bounding boxes for units. So when you move your units around in the game of Starcraft, they're actually moving at a pixel resolution, right? So the smallest level that you can possibly have in the game. So these units can be placed arbitrarily. However, when the game goes to compute whether or not a unit can walk somewhere on the map, it uses this gray grid here. And this gray grid is of a resolution of 8 pixels high by 8 pixels wide. So these cells are squares of 8 by 8 pixels. And the reason for this is because if we stored the entire map's walkability values, and by walkability I mean can I walk here, or is this a wall, or is it a cliff, or is it blocked, or something like that, it would be way too much data to store that on a pixel by pixel level. So inside the game, it splits this up into these 8 by 8 pixels. Then, on top of that, there's another size of grid, and that grid is the green one that you see here, and that is the build tile resolution. And so when you go to place buildings on a map, those buildings are placed at that resolution, which is 32 pixels by 32 pixels. And you can see here that it encompasses 4 by 4 of the walkability tiles, okay? So now we're kind of seeing how, even though grids are a simple data structure, you can sort of layer these things, you can have different abstractions, different resolutions of these grids, and they can accomplish different tasks within our game. So just as a little recap here, Starcraft has 3 different precisions for its grids. The first type is the pixel level resolution, which is just 1 by 1 pixel, and the units move in the game at that grid resolution of 1 by 1 pixel. Next, there's the walk tile, which is 8 by 8 pixels, and that's the gray grid over here. It's a sort of Boolean 2D array and says whether or not you can overlap that tile with a unit, and you can't overlap tiles that are false. And then we have the build tile resolution, which is 32 by 32, these green ones over here. And the buildings have to be placed in a rectangle, a contiguously available rectangle at the build tile resolution. And you can't place on an unwalkable tile either, because if you can't walk on that place, then you probably can't build a building on it. All right, so that was Starcraft. It turns out that Dragon Age also has a grid-based system for its pathfinding. And this is a screenshot of the original Dragon Age. I know there's been lots of games since then. But in this game, you do have a grid. That grid can have cells that are blocked by world geometry, and then the pathfinding is done at that grid-based level. Okay, so similar thing, completely different type of game, but a similar type of system for its space representation. And a nav mesh could also be grid-based, right? So navigation meshes, by definition, have an arbitrary graph structure, but they could be set up as grids like we saw last time in this example. And the reason for this is because grids are just a special case of a graph, right? So grid is a graph where the nodes are connected by edges, and those edges are like up, down, left, and right type of movement. Okay. So one of the considerations that we had before was talking about localization. And so localization is essentially how do we actually locate ourselves or an object or an entity within our representation, right? So entities in a game generally have real valued coordinate system, right? So for example, even though Starcraft has these grids that it uses for the locations of enemies or the locations of units, you're still living, like internally, you can still represent the location of an object as a real valued number, right? So maybe I'm at X value 22.7 and Y value 12.4, for example. And just because your in-game representation has like an arbitrary floating point precision doesn't mean that you can't use grids. It just means that we're going to have to do some sort of translation from one space to the other, right? So over here, I have an example. let's say this is our example game over here, and in our game, we have arbitrary locations for our units, right? So this purple one is down here, this one is sort of in the middle of this cell, or over here, this one is in the top right of the cell, but we've overlaid a grid on top of this world, right? So if we're going to use grids for example, for our pathfinding system, the first thing we have to be able to do is translate from the actual game world coordinates, and this again might be like 100 in the x direction and 500 in the y direction, something like that. And we must be able to translate that into the location on our grid that we've overlaid, right? So there's a few ways that we could do that. We could do like truncation or rounding. We could divide by the grid size. So there's all sorts of different mathematics that you could use to translate from a real world position to whatever grid position that we have. So here's just an example. Let's say in our real game, we have an entity that's living at position 23.6 in the x direction and 44 in the y direction. And what do those values mean? Well, those values could literally mean anything. That world could be infinitely big. It could be size 100 by 100. It doesn't matter, right? We just have a unit that's living at position 23.6, 44.4. And let's say that we have a grid overlaid on top of that world, and the size of each cell of that grid is 10 by 10 pixels, right? So if we have a position at 23.6, 44.4, and we want to translate that into, for example, which cell is our entity living at, well, let's just do a quick example up here with these, right? So let's say we want to know which cell is this yellow object living at. Well, we would count over in the x direction, so 0, 1, 2, 3. So that's at 3 in the x direction. And then we count in the y, 0, 1, 2, 3, 4. So this entity, regardless of where, like what the position is in the game world, it's in the cell 3, 4 in our grid representation. So the way that we would do that is if we have a certain position in the game world and we have a grid size, for example, we can just do integer division. Okay, so 23.6 would be divided by the x size of the grid, which is 10. And so 23.6 divided by 10 becomes 2. And then 44 divided by 10 would become 4, right? So essentially, if we look over here, so over here, let's say if these grids here were 10 by 10 grids, let's see what is the position of this green entity down here. Well, in the x direction, it looks like they're about here in the x direction, right? So that would be 10 and maybe 6. So that would be like 16 in the x direction. And then in the y direction, we'd have 1, 2, 3, 4, 5, 5 and a bit. So we would have 67 in the y direction. So something that's at 1667, that will be translated into grid cells 0, 1, 2, 3, 4, 5, 6 in the y and 0, 1 in the x, okay? So that's pretty intuitive. I know I've explained it to death here, but we're going to have to be doing this in our assignment, so I wanted to make sure that you understood that. You're just translating your real world coordinates into the actual grid cell coordinates. Now, we could have the simplest possible case, which is actual grid world games, right? So over here, for example, we see Civilization, which does have a grid, but it's a hexagonal grid. And down here, we see an example of an older arcade game called Qbert, which sort of lives on this grid as well. But so some games already take place within a grid, right? So we don't need to do that translation. These grids are not always squares. So be aware that grids don't have to be squares. And so these grid world games, they don't need any translation. Everything lives within that grid cell anyway. And so the game space and actions of these games are completely defined by the grid. But this is sort of an obvious case of, all right, well, that's not every game, right? We don't need to worry if it's already in a grid. Let's just go back to the examples of when the games aren't naturally in a grid, but we're going to use a grid representation for our AI system, okay? So let's talk about a task location grid. We saw an example of this in Starcraft. I'm going to let... Okay, so a task location grid, as we might see over here, is used to determine on which tiles we can perform some desired task, okay? So for example, whether or not we can walk on a specific tile, whether or not we can build something on a specific tile. So over here, this is an example of a task location grid. And I want to make my camera just a little bit smaller, so give me a second. Okay, oops. So over here, we want to build a task location grid for walkability or maybe building, for example. So let's say we're talking about building in this example. Over here, we have these yellow objects in our game. So we have this little triangle down here, and we have this big polygon up here. We have overlaid a grid on top of this environment. And here's the grid structure that we have, and it just happens to have the properties of being this large. So if this is like an obstacle in our game that we can't walk through, for example, or we can't build on, then essentially what we have to do is we're going to have to identify the cells in our grid that this thing overlaps, and then set the values of the task location grid to say we can't do that specific thing at that grid size, or at that grid cell, okay? So initially, this entire grid is going to be set to true, okay? So we can do anything anywhere. And then what we're going to do is we're going to loop over each object in the grid, which blocks a given task from being completed, and then set the underlying cells to false. So what that means is for every entity in our game, if this is like a blocker, right? So if this is like a big rock in our environment, then we would compute which of the cells that this thing overlapped, okay? And then we would turn those cells to false in our task location specification. So what we can do now is that the grid can now be used as a constant time lookup table to check if a task is possible. So before, what we would have to do maybe is, if we wanted to build something, we would have to take the size of our building, we would have to check it against the bounds of this object, maybe that's a rock, and that geometrical check is going to take a bunch of time, right? We're going to say, okay, well, the four sides of this building, does it overlap with like any of the sides of this building? And that's sort of an expensive geometry check. But if we use this task location grid, then what we do is we have pre-computed which cells I'm able to do something on. And now all I need to do is check, okay, can I do it in that cell? No, I can't. And so we've changed this sort of expensive computation into a constant time lookup within our grid. And so just note that in some games, we may be trading accuracy for speed of computation. And what do I mean by that? Well, if we look up at this, we are definitely making some sort of abstraction that's not exact, right? Because in the real world, not a video game, but in the real world, I would be able to build a building something like right here, right? I'd be able to build something right here because technically it is not overlapping with this structure. But in our grid representation, depending on the size of the grid, I can't build it there, right? I would have to build it down here somewhere where all the cells are unoccupied. So this abstraction, which makes some computations very quick, comes at the price of exactness. Okay, so just remember that in computer science, we're always trading the quality of our solution with the speed and the memory usage of our implementation. So one of the possible ways that we could, let me just go back here. One of the possible ways that we could try and alleviate that problem would be, if we look over here at the grid, would be maybe to, okay, well, we want it to be more accurate. Let's cut our grid up into smaller chunks, right? So we'll make it a more fine-grained grid. Well, what we're doing then is we're trading memory for accuracy, right? So if we double the precision of our grid, we double the memory usage, essentially. Okay, so let's keep going. So in StarCraft 2, and in StarCraft, and in Warcraft, This is literally what the game engine does. It takes the world and it chops it up into this build grid. So if you've ever played one of these games and you click build, this is exactly a screenshot from the game where I'm trying to build a command center in Starcraft. And so the game internally stores this representation as a grid. So as I move this around the game, it's trying to find where to build it in the map. And in Starcraft, for example, if it's red here, it's saying, well, you can't build it there. Well, why can't I build it there? Because in this specific case, this is going to be built too close to some resource patches, for example. So I might have to move this to the left or the right, and it'll turn green when I can build it. So it's a very nice user interface for the player as well. The Warcraft 3 build grid is very similar. It's a little more 3D than the Starcraft version, but, well, it's 3D in its rendering, but it's still a 2D grid representation, okay? So what does this look like in the game? It looks something like this. So I'm trying to build a building, and here I can see when I'm trying to build this gateway, if it's overlapping with one of the walls, I get a little red X, but if I can actually build it there, then it'll be green, right? So there's certain places in the map that I can build it and certain places that I can't build it. Now, this doesn't mean that this is how you have to implement your game, right? Let me play this again. So you can see how it's red here because it's overlapping the wall, and so we move it over until we can actually place it there. This doesn't mean it's how you have to do it. You could build things at an arbitrary level of precision if you wanted to, but again, that may take more space, that may take more memory, your algorithms may take a little bit longer to run, okay? So this is just an example of that. Okay, so in general, when you're trying to do this task location grid, filling the grid may involve computing polygon edge line segment intersections with the grid lines. So what does that mean? Well, it means that what we're going to have to do in general is if we have arbitrary polygons in our map, right, then we're going to have to take every edge of that polygon, that line segment, and try and compute where it is on the grid, and that may involve some line segment intersection calculations, okay? However, if we restrict ourselves to rectangles instead of arbitrary geometry, we can do some really cool optimizations. So in the case of axis-aligned rectangles, which means they are parallel to these grid lines, we can optimize this computation to be much, much faster, okay? So this is what we're going to be doing in assignment 2. So in assignment 2, we're essentially going to be making our own grid-based navigation mesh for some environment that I'm going to give you, okay? Inside that, actually, why don't I show, I can't show it to you right now. Can I? Yeah, let me show it to you. Just give me a second here. I think I can. All right, so this is a little sneak preview of assignment 2. Let me make that bigger. Here we go. So in assignment 2, we are going to be making this like navigation mesh type system in which we have obstacles. So these rectangles in our environment are going to be blocking areas that we can move in, okay? And what we're going to be doing, I have a little help system here because I forget the controls sometimes. Let's do. All right, so I got A, D, and G. Okay, so here, what we're going to be doing is we're going to be making a vector field pathfinding system, and we're going to have particles living in this space, and they're going to be doing some pathfinding, okay? So we can see here that even though these rectangles have like an arbitrary precision where they live in the game, we want to compute our own navigation mesh so that our particles can actually get to the goal location, which is this yellow location down here, right? So in real time, we are calculating this navigation mesh, and so watch, if I take this rectangle and if I extend it so that it blocks this area, now the particles can no longer pathfind in that area, right? And again, if I extend it over here, then they have to take the long way around. So in real time, we are going to be making our own navigation mesh based on these rectangular objects that act as obstacles in our game, okay? So it's going to end up being pretty fast. In my solution, I can do hundreds of thousands of these particles. I know my bit rate probably just went way down, but this is essentially assignment 2. So I wanted to show you the context for that. And not only that, but we're going to be able to arbitrarily change the size of our grid as well, okay? So I can make the grid more fine-grained. And so here we can see that if we have like a huge grid, well, this isn't very accurate, right? Because look at this. The grid size is so big, and I'm considering these cells as being blocked off in my navigation mesh, but in actuality, these particles can probably travel between these two rectangles, right? So, but the good thing here is that the grid is so big, the algorithm doesn't take long to run. However, if I make my grid bigger, without moving the rectangles, now we have a finer grained navigation mesh, and so these particles can now spawn and move down here, okay? So this is assignment 2, and this is the context for this lecture and the grid algorithm that we're going to be doing. Okay, so let me go back to the PowerPoint. So here is how we're going to be computing the navigation mesh or I guess in terms of task location, we're computing a task location grid where the task is being walkable or not, right? So let's compute that. And in our environment, we have the benefit of using axis-aligned bounding box rectangles. So that means that they're just rectangles which are completely aligned to the grid. However, there's a really cool optimization that will make this really, really fast. So how do we compute which cells are being blocked by this rectangle? Here's how we can do that. First, what we're going to do is we're going to compute the cell, so the XY location of the cell of the top left corner of the grid, okay? Or sorry, of the top left corner of the rectangle. So if we are given this rectangle here, right? There are many ways that you can actually represent a rectangle. You could be given the XY location of the top left and the XY location of the bottom right, or you could be given the XY location of the top left, and then you could be given the width, and you could be given the height, okay? What I'm going to assume here is that I've given you this rectangle as the XY location of the top left and the XY location of the bottom right, okay? So we're going to take that top left location, and that's going to be called TL. So TL is the top left of the rectangle. And we want to compute which cell in our grid representation does the top left of the rectangle overlap with. Well, that's really easy to compute because we just have to divide the x-coordinate of the rectangle by the size of our grid. And here we're assuming that we have a square size, right? We're going to have squares for assignment 2. So this CTL, that is the cell top left, okay? So cell top left, excuse me, I got cat hair floating around my room. The cell top left, the x-coordinate of that is the x-coordinate of the top left of the rectangle divided by the grid size, and then the y-coordinate is the y-coordinate of the top left coordinate of the rectangle divided by the grid size. Then we're going to compute the bottom right corner, okay? So which cell does the bottom right corner of the grid overlap with? Well, it's the same thing, except we're using the bottom right coordinate of the rectangle instead of the top left coordinate. So the cell of the bottom right is the bottom right coordinate, x-coordinate of the rectangle divided by grid size, and the bottom right y-coordinate of the rectangle divided by the grid size. And then you might say, okay, well now we're going to have to do a bunch of line intersections. No, you don't have to. No line intersections are necessary because all we have to do is do a for loop from this grid cell all the way over here to the x-coordinate of this grid cell, and then we can fill out all of these grid cells and mark them as blocked. So we just loop over the x direction and we loop over the y direction from the top left to the bottom right. And so we loop from the top left to the bottom right and we mark each of these cells as blocked. And that's exactly what we do in the assignment, okay? So this is, you're going to have to implement this part for computing the space representation, which is the navigation mesh or grid of our environment. All right. So that's a cool optimization that we can do if all of our obstacles are perfect rectangles. Now, if you're making a more complex game, that's not going to be the case. But I mean, we're not going to make a whole pathfinding system for a real game for one assignment in our course, right? We're going to make these abstractions and do these cool optimizations. Alrighty. So grid movement now. We've talked about how to represent the grid. What about actions within the grid? Well, if we're using grids for pathfinding, then typically what we're saying is that movement in the algorithm that we've chosen to use for our grid is restricted to adjacent traversable cells. Okay? So, for example, over here, I have this object, this red object, and it can currently move up, right, or down. So we could have 4-directional movement like this, and if we have 4-directional movement, this object cannot move to the left because that grid cell has been marked as blocked for whatever reason. Here we might have 8-directional movement, right? So we can move in 4 up, down, left, and right, as well as diagonals, but we can't move to these cells because those cells have been considered blocked, okay? And so, of course, there will be like exceptions if we have games with teleporting or blink type abilities, etc. But let's just talk about like basic movement for now. So our legal actions for grids, if we are restricting ourselves to cardinal movements or just up, down, left, and right, then we have those 4 actions, up, down, left, and right. Or we might have octile movement, which is 8 directions, so that's up, down, left, and right, and then the diagonals in between those, okay? So if we're talking about pathfinding within these actions, you may be sick of this diagram if you took 3200 with me, but essentially we're going to have to choose some action representation for the movement in our pathfinding system. Okay, so just keep in mind that even though movement in our actual game may be completely arbitrary, meaning that we can move at any angle, if we are using a grid representation to compute the pathfinding, then there has to be a more abstract representation of those movements within our pathfinding system, okay? So just because we restrict our pathfinding algorithm to up, down, left, and right, that doesn't mean that eventually the movement that gets implemented in our game engine is going to be up, down, left, and right. And I'll show you how that is. So, but the path may be affected by this. So for example, if we chose a grid representation and we chose 4 directions for our path, then we may end up with a path like this in our game engine, which sort of like follows these blocky type movements. If we choose 8-directional movement for our games, then we're going to be moving around in grids like this, right? So we can use octagonal or diagonal movement in the games for our shortest path. So that's just showing you that you need to choose some way of moving around in the grid for the algorithm that you eventually choose. So 2 of those more common ways are 4-directional movement or 8-directional movement. Okay. So let's talk a little bit more about these grid cells and specifically how these grid cells are going to work for assignment 2. And, well, in our course at least. So the grid that we overlay onto an environment can have an arbitrary size, right? It could be rectangles, it could be squares, you could have 1,000 in the X direction and 200 in the Y direction. It's up to you how you choose to implement this. But each cell will have a position. And so we're going to refer to the cell position by its XY coordinate essentially in the 2D grid, okay? So for this course, X is going to increase from left to right. So this is the 0 column in the X direction. This is the 1 column in the Y direction, okay? Or in the X direction. And Y is going to start, so 0, 0 starts in the top left, X goes to the right, Y goes down. So here, this would be 0 in the X and 2 in the Y. This would be 2 in the X and 1 in the Y, for example. So actions in our grid are represented by the change in the X and Y coordinate of the cell that we're using in the grid, right? So if we are at a current XY location, then if we want to move up in the grid system, that's a change of 0 in the X and -1 in the Y. If we wanted to move down right, that will be a change of 1 in the x and 1 in the y. So when we talk about actions in a grid-based system, we are talking about the change in the cell of movement, okay? And that's represented by an xy change that you see here. Depending on the algorithm that we are implementing, if you remember back to 3200, which is a prereq for the course, our actions also had costs, okay? So a diagonal action moves a little bit further than a cardinal action, and so those actions are a little bit more expensive. Some algorithms do not have the notion of cost, but we'll see some of those algorithms in the next lecture. So just realize that you may also have a cost associated with actions. I found a little cool example of a 3D game that uses grid cells for its pathfinding system. So this is called Trudy's Mechanical. And what happens is it's a 3D game. However, tiles are sort of stacked on top of each other. So a top-down view of the game is still a two-dimensional grid. And so the way that the navigation mesh in this game works is that you can go from one cell to another cell as long as it's adjacent and it's not too high up, okay? So for example, you can move from this tile and like up onto one little step up here, but you can't jump from that tile on top of this wall up here, right? So it incorporates a grid system for pathfinding in what's actually a three-dimensional game. So you could use this sort of system for pathfinding in a more complex game. So grid pathfinding. We've talked a bit about pathfinding so far, but one of the most common uses for grids is for pathfinding. And the reason we use grids for pathfinding is because our grid is a more abstract data structure, and there are fewer positions and actions to consider in the algorithm if we're using a grid than if we use the native game world space, which may be like arbitrary floating point precision. So how do we do grid-based pathfinding in a non-grid world, right? So I want to show you that I kind of alluded to how this would happen in the last class, but I want to show you now sort of the full process that you would use on how to actually take an arbitrary precision game world, like this one, and implement a pathfinding system that actually uses grids in that game. So here we have a game world, and we have two locations. So these locations are up here and down here. Those are arbitrarily positioned, okay? So this might be 3.14 and this might be 6.23, okay? They might be completely real valued positions. And then we have some obstacles in the game that have an arbitrary geometry. Doesn't really matter. So first is we have an actual game world. Next thing we do is we're going to define the type of problem and the goal that we're trying to solve, right? So I may want to get from this location up here in the top left to this location down here in the bottom right. However, I can't do that. I can't walk straight because there's this big obstacle in the way, okay? So what we do is we choose a grid to overlay on top of this world. I just so happen to have created this grid to almost, to really well match up with the geometry of this. It won't always work out this well, but you're just going to choose some grid size to overlay on top of your world. Okay? Then what we do is we set the grid values for whether or not we can actually walk on specific tiles of this map. So once we're done setting these grid values, so we would compute the geometry of this obstacle, we would compute which grid cells it overlapped with, and then we would mark those grid cells, okay? So just keep in mind that we are losing some precision here, right? So whereas this is the actual walkability in the real game, we have this abstract view of where we can walk in the grid cell representation. And again, if our grid was a little bit smaller, so if it had more grid cells, then we could increase the resolution and increase the accuracy, but that would be at the cost of speed and memory of computation, okay? So now we've set our grid values, which basically say we can only walk on the blue tiles, right? We can't walk on any of these green tiles. So now what we do is we use that little algorithm that we had to translate the positions of these units into their respective grid cells. So here we go. I'm at this starting grid cell, and I'm at this goal grid cell. I'm going to then choose an action representation for my pathfinding system. So in this case, I've just chosen up, down, left, and right for my actions in my pathfinding system, which operates on the grid. I'm going to run my pathfinding algorithm, and it has magically come up with a path for me. We're going to talk about algorithms more in the next lecture. Then, from that algorithmic path, I'm going to generate path waypoints in the grid cell space. Then, I'm going to translate those waypoints back into the real game world coordinates. Okay? Then, based on what we saw last time, I'm going to refine the path in the game world so that it's a little bit nicer to work with, right? I don't want this like L-shaped stair-like paths in my game. I want it to be more straight lines, okay? Then I implement path following in my game with something like a steering system so that it looks like it's nicely, smoothly transitioning, okay? So this is the entire system. It's like 11 steps, so, you know, it's not super trivial, but it's not that hard either. And it just shows you how you can do pathfinding in a grid world and then translate those paths back into this arbitrarily action-spaced world and have the paths look pretty cool. Okay? All right. So this course is written in C++. How are we going to actually implement these things? Well, in assignment 2, what we're going to have is a grid class, okay? So a grid class is essentially a wrapper, or it's a class that is a 2D array, okay? Or a 2D vector. So what we're going to do is we're going to have a vector of vectors of whatever type. So this is a templated grid class that can store any type. So we could have a grid of integers, a grid of floating points, a grid of doubles or booleans or whatever we want. Okay, we're going to have a constructor, so we could take in like an x and a y value for the size of the grid. So I could say 100 in the x, 20 in the y, and then give it some initial value to fill up the grid with. And then we could have like operators, like we could get values in the grid, we could get the width and the height, etc. But for assignment 2, and I'll show you more of this when assignment 2 rolls around, we're essentially going to be working with this grid class, which is a 2D array type structure. So now that we've shown this sort of process, what are the advantages and the disadvantages of this? Well, one of the advantages is that it's very easy to implement, right? Everybody, especially at the senior computer science level, could implement a 2D array or a 2D vector. That's really simple. And assignment 2, I'm actually giving you the data structure, so it's even simpler. They're very easy to visualize, and they have an intuitive usage. They're very quick to modify for dynamic changes. So if one of my obstacles in the game moves, I just update the grid cells. Really easy. Arrays are very, very cache friendly. Cache friendliness is very good. If you want to get a good time in assignment 2. So assignment 2, we're having an in-class competition to see who can compute it the fastest. And you're going to have to be very cache friendly if you want to have the fastest time. It's very easy to specify and understand the actions, right? Because let's say if we had an arbitrary graph structure, one of our actions might be, okay, you can move from node 32 to node 41. Well, what does that mean? What does that look like? It's very difficult to intuitively see that. And so in grids, you can say, well, we're going to have up, down, left, and right. Or we're going to have 8 directions. Or we're going to have any adjacent cell. Or any hex that's adjacent, right? It's really easy to specify that. And pretty much any graph search algorithm that exists will also work on a grid. However, there are some algorithms that only work on grids, right? So all of you are probably thinking, oh my God, is he going to have us doing A star again, right? Because all of you have done 3200. So in Computer Science 3200, we use the A star search algorithm to compute our grids, or to compute our paths. A star can be run on an arbitrary graph, right? However, we're doing something else which is going to be called vector field pathfinding in this course for assignment 2. And that algorithm can only work on a grid. It cannot work on an arbitrary graph. Okay? So these are the advantages of grids, is that we have some algorithms that can do really, really well on grids. They're easy to visualize, et cetera, et cetera. What are some of the disadvantages of grids? Because in computer science, nothing is perfect, right? There is always advantages and disadvantages to everything. So one of the disadvantages is going to be localization, okay? And that means that there's always some level of abstraction when we translate from a grid position to a real-world position. So for example, here, the path that we would compute in the grid to get from here to here would kind of like move all the way to the right and then back a little bit, right? Because we may be choosing the center of our grid cells as the waypoints. So let's just say that we computed the grid here, and we have a waypoint here, a waypoint here, a waypoint here, a waypoint here, a waypoint here. Then the path would be like, it'd be a little bit jagged at the end, when in actual fact, what we wanted to do was have a path that's more like this, right? So localization can be a little bit of a nuisance. We have to be very careful about how we specify actions, about how we do the translation, and how we set up the waypoints. Okay, so just make sure that you're doing what you should when it comes to localization. Also, the grid abstraction may lose precision, right? It's going to lose precision. Let's be real. Game entities may have real valued positions, and you just lose all of that precision when you translate into a grid. The complex geometry of your game world may not be captured very well, right? So rectangles do not encapsulate all the shapes very well. So for example, if you use my hand as a shape, there are spaces in between my fingers, right? Where a bullet might be able to go if we're talking about physics. But if we had a grid-based system, it would just like completely lose all of that sort of detail. And so we want to use grids on these sort of high-level, less precision calculations like pathfinding versus like bullet physics and stuff like that. And the real disadvantage of grids is that the memory usage of grids for large spaces can be very high, okay? So grids are inefficient for sparse spaces. And I'll show you an example of this. So for example, if we just have a big level with only a few blocked cells, let's say we may have like, okay, let's give an example here. Here is an example map from Dragon Age, and this is from the Orzammar area of the game. In the actual game, there are 96,000, so about 100,000 walkable tiles in this area. But in total, there may be hundreds of thousands, if not a million, tiles that you can't walk on, right? Because a grid is a 2D structure. So we've got a rectangular grid like this. Only some of the areas are actually walkable, and a vast majority of it is not walkable. And so we call this a sparse representation. And just keep in mind that sparse representations are sort of the worst case scenario for memory usage for grids. Here's another example. We have Dragon Age Origins. Again, where we have this like sparse representation for a cave-like structure. And in the original Starcraft, we have a 1,000 on average, or I guess this is the worst case. So the biggest maps in Starcraft have a 1,024 by 1,024 walkability grid. So that's 1,000,000 cells in the walkability grid for a Starcraft map. Okay, so just keep all of this in mind when you're choosing the representation, especially when you're choosing grids. So we talked about our representation, so localization, generation, dynamic changes, planning and pathfinding, memory and speed. So we've got a bunch of different representations. We're going to cover as many of these as we can in the course. But first, let's talk about grids. Okay, so for grids, localization is very easy and it's very fast, but we may lose precision, so it may be inaccurate. Dynamic changes are very easy. Okay, we can just update grid cells like in constant time since they're just array lookups. Our planning speed is going to be relatively low for single paths, okay? Because like we may have a lot of grid cells to look over, versus if we had a waypoint graph, there may only be 100 waypoints where we had 100,000 grid cells, right? So the planning speed is relatively slow, but the memory usage is very high, okay? Because we have to store a bunch of data in these cells that we may not necessarily need. Okay, and we'll see as we go through the course, hopefully, what the rest of these properties are. Okay. So grids take a lot of memory. Let's see what people have done to try and abstract away those problems or try and solve those problems. Large grids take a lot of memory and potentially hold very, very few values, right? So large grids also cause algorithms to potentially run very slowly and cost more memory. So like I said, Starcraft maps can have up to 1 million walkability cells. So if possible, we want to avoid such large grids, but could we still use grids for really, really large spaces? So some of the things that people have done in the literature for like actual, if you go on to grad school or you're trying to implement a really complex pathfinding system, is have ideas of abstractions on top of abstractions. So let's say we have a grid structure, but now we're imposing a grid structure on top of the grid structure. So it's like a hierarchical grid, okay? So what you do is you have a grid structure, you break this down into like a more coarsely grained grid, and then you impose like a graph structure on top of that grid. And then you do pathfinding in the graph, and then later, once you have the path in the graph, you come back and refine the path in the grid, okay? So like there's all sorts of really cool research that goes on in the academic literature about pathfinding and heuristic search and all that when it comes to dealing with these problems. And, whether or not these things make it back into industrial, like actual industry, retail video games, who knows? But just saying that just because grids have a couple of negative properties don't mean that we're never going to use them in real games. What are some more optimizations that we can be done with grids? Excuse me. So one of the downsides of using grids is that we lose precision because we have this sort of fixed structure, right? But in computer science, if we fix a structure, usually now we can tailor our algorithms or maybe do some pre-computation to speed up our calculations once we have a fixed structure. Remember in assignment 2 of 3200, how we did all of that pre-computation and everything got a lot faster, like the sector-based computation? With grids, we can do a lot more stuff like that. So smart choices on how we store grid data can reduce memory usage significantly. So, for example, instead of checking legal actions during the running of the algorithm, we could pre-compute a grid that stores the XY legal actions. So I showed this in 3200, right? So for example, let's store a separate grid which pre-computes which actions are actually legal at each cell in that grid. So for example, for 3200, we showed that like in this cell, the only action that's legal is moving down. So we would store this value as the vector of actions that are legal from that cell. Here, the legal actions are up, right, down, and down right. So what we've done here, we've used a little bit more memory in order to pre-compute legal actions so that we don't have to dynamically compute legal actions during our search algorithm. Then what we could do is we could also, and I could do this for assignment 2 if you wanted to, is if we look at this, this takes up a lot of memory, right? Because each grid cell could potentially have 8 values stored, but each of those values is 2 integers. So an integer is 4 bytes. We've got 2 of them each, so that's 8 bytes per direction. And then we could have up to 8 directions. So that's 8 times 8, 64 bytes per grid cell. If we're talking about 1 million grid cells, that could be like 64 megabytes just to do this pre-computation. That's a lot of RAM. We don't want to use up that. So let's talk about a grid optimization that we could do in this case, okay? And I'm just throwing out these as, you know, sort of wink, wink, nudge, nudge ideas for assignment 2. All right. So let's assign a value to each direction in our legal actions, okay? So over here, I have an index, and this just says up here above where my webcam is showing, it says direction. So moving down, moving up, moving left, moving right, and all the diagonals, we're going to assign each of those to an array, right? So I have a vector of these actions. It's of length 8, and the index here, this integer, is the index into that array for each of those actions. So now instead of storing a direction of 2 integers, I'm just storing an index, okay? So each grid cell must store a maximum of 8 directions in that container. Remember? Like this could have 8 legal actions. In this case, it only has 5, but it could have up to 8. So one direction is an integer, which is now 4 bytes, right? Because I'm storing as an index. So 8 bytes for 2 integers times 8 is 64 bytes per cell. The container may have some overhead too. But for only 8 directions, we don't necessarily need an integer for this. Let's see how we could optimize something like this to take up far less memory, okay? Let's try a bit set. So a bit set is something that we can do in C++. So in C++, a char, or a character, is essentially an 8-bit or 1-byte integer. So a char has 8 bits that it can store information in, okay? I have 8 bits. 8 bits, 8 directions. Interesting. What could I do with that? So, given an array or vector of all the possible actions, okay, each one of them has an index that we can refer to from 0 to 7. So we've got an integer associated with an action. Instead of having a vector listing all of the directions for each grid cell, how about we use a bit set, a character bit set of length 8? And so the bits in that character in the bit set essentially mean if we have a 1, it means an action is legal. And if we have a 0, means an action is not legal. So here we have bit 0 is 0, bit 1 is 0, bit 2 is 1, bit 3 is 1, and so on. So 0011, 0001 means that all the bits with a 1 are legal. So actions 2, 3, and 7 are legal. So if we have now just a 1-byte character in each of our cells storing this bit set, if we had a cell that had this exact value, it would mean that the actions of going right, going left, and going down left would be legal. See how that works? So it's really cool. We took 8 actions, 8 bits, 1 byte per cell. So before, we had 64 bytes per cell if we were just naively storing all the actions. But now what we have is we have reduced memory usage by 64 times by using bit sets, okay? So this is just like a very start of the deep dive of stuff that you can do for optimizations for assignment 2. And going from 64 megabytes to 1 megabyte of memory for pre-computations is actually really huge. So that's it for that's all I wanted to say about using grids. You could write PhD theses on the usage of grids in games, but I'm not going to go too much deeper than that. And in the next lecture, I will go over grid algorithms. Not all of the grid algorithms that exist, but specifically the things that we're going to be using in this course for assignment 2, and possibly things that you could use for your project as well. Alrighty. So that is it for today's class. So that was space representations. And in the next class on Thursday, we will go over grid algorithms. And then the quiz that is released on Thursday will be covering today's lecture and that lecture on Thursday. So thank you very much for tuning in, and I'll see you in the next one.